Creation of a high-temperature plasma through merging and compression of supersonic field-reserved configuration plasmoids. Number 5. Discussion and conclusion. With the successful merging of supersonic FRC in the IPA experiments, a method with the potential for the production of fusion energy in a simple and technological appealing manner has been demonstrated. FRC plasmoids were brought to high temperature and density via a linear sequenced array of low field compression coils, establishing a means for obtaining fusion conditions remote from the plasma formation system. To obtain the requisite Lawson product, a larger FRC must be formed, accelerated, and compressed to higher field from the result of the IPA experiment together with equation 10. Break-even conditions will require an increase in colloidal flux, which can be achieved by a radial scale increase of roughly a factor of 3 to a formation size, similar to the LSX experiment. The merging chamber would remain at 0.1 meter radius, but at much higher field, 10 Tesla. The same magnetic kinetic compression scheme as used on IPA would be extended in order to impel the FRC into the higher field of the burn chamber. The sustainability of this approach to fusion or fusion-fission hybrid application is the consequence of the numerous critical advantages that significantly reduce the technological challenges as well as the cost of development and operation. The more significant begin with the ability of the FRC plasmoid to be translated and merged where the FRC formation and kinetic energy input is added outside the burn chamber and realized only within the burn chamber, as demonstrated in the IPA experiments. The plasma diverter region is well removed from the reactor and can be scaled to eliminate any power loading issues, with the diverter located remotely in an essentially neutron-free environment. Tasks such as full tritium recovery and diverter maintenance are made much easier to perform in order to rapidly span additional fusion system, maintaining a low tritium inventory and creating more tritium than consumed will be essential due to the pulsed FRC reactor's linear cylindrical geometry and the small scale of the fusion plasma compared to the neutron absorption. region. The breathing blanket coverage can be optimized. It is critical that a sufficient number of energetic neutrons interact with lithium in the blanket to breed new tritium fuel. A high conversion efficiency of the first fusion neutrons in the blanket surrounding the device makes significantly more fusion neutrons available for both fuels and fissile fuel generation as well as waste burning applications. The simply connected linear geometry of the reactor vessel is also unable to rapid and frequent first wall replacement if necessary, and fluid metal wall interface in this geometry is also possible. This would allow for operation at the highest power density and resolved several plasma material wall issues. There are also several critical attributes related to the unique nature of the FRC as the fusion plasma reactor cost will generally scale inversely with the fusion power density, which in turn scales as beta square b to the fourth power. The FRC has the highest beta of all magnetically confined fusion plasma, and the simple cylindrical nature of the confining field coils provides for the highest magnetic fields. Utilizing the FRC plasmoid for magnetic fusion energy thus represents the highest fusion power density that can be attained in a non-destructive, repetitive manner. As indicated in Figure 10, the small ratio of the FRC volume to the neutron absorbing blanket volume provides for the maximum fusion power density obtainable without exceeding thermal limitation in the blanket for hybrid operation. The small footprint allows for easy integration into exciting fission power plant infrastructure. The reduced reactor scale also means much faster and far less expensive interactions during the development phase, which will be essential to the integration of improvements and new technologies. At first thought, it would appear that a pulsed system would be inferior to a steady system, primarily due to the advantages of self-sustainment. There are several limitations imposed by a steady fusion burn, not the first being constrained to an inherently low power density. as is now being realized, the steady band does not easily allow for maintenance of the plasma wall interface. The ability to maintain the critical balance between alpha heating and plasma loss in an ignited reactor is an open question, as is tritium retention, fueling burn. Diagnostic plasma current sustainment, profile control, as well as several other device specific issues such as disruptions by virtue of the cyclic nature of the burn. Virtually all those issues are eliminated or significantly mitigated. Both fusion reactor gain and diverter wall loading can be readily regulated by the compression stress and REP rate R. All of the DT fuel can be introduced during the initial formation of the FRC plasmoids, eliminating the need for refueling. The major challenge for pulse system is operation at the highest efficiency possible in order to minimize what would otherwise be a large recirculating power fraction. Using pulses magnetic force to form, accelerate, and compress the FRC to fusion conditions is efficient with ohmic losses in the drive circuits as the primary loss channel. Employing a pulsed magnetic field also affords a unique opportunity for direct energy recovery. It has been appreciated in the past that pulsed systems employing flux compression can realize direct recovery of the fusion alpha energy. For the pulsed compression of the FRC, this task, the form of the black EMF experienced by the compression circuit due to the increase in FRC plasmoid pressure from the presence of the fusion alphas. This pushback during the neutral oscillatory behavior of the compression circuit causes the energy storage capacitor to the recharged to greater energy from the increased expansion energy of the FRC. A key technology for such a system is the use of an opening switch to allow this energy to then be stored for the next pulse. This appears feasible as the voltages and energies envisioned for the prototype are within the range of what can be achieved with current solid-state switches and power delivery systems. Additional recuperative operation of all the magnetic field circuits would provide for a way to significantly reduce the energy losses to primarily that of the FRC itself, even that energy may be recoverable in some measure by direct conversion in the diverter, as the plasma energy loss is primarily in the form of a high energy directed plasma jet at the diverter entrance. The capability to make use of the plasma fusion and electrical energy in an efficient manner is unique to the concept described here and is critical for the commercial application of fusion to be realized without resorting to a large-scale, higher fusion gain system. Possibly the most underappreciated advantage of a pulse system comes from the ability to evaluate key performance milestones with single pulses. This minimizes neutron activation during development and further reduces cost as much simpler and less robust pulse power system can be employed given the scaling and the desire to optimize at smaller radius, and higher power can be employed given the scaling and the desire to optimize at smaller radius and higher power density. It is worth determining the parameters of a device capable of a gain of 5 from equation 10. The following values will yield such a gain. LS equal 2 meter, phi equal 25 milliweber, BE equal 16 Tesla, Q equal 5. With the compression coil radius RC equals 0.2 meter, the FRC should remain well below the kinetic stability limit given in equation 12. Even prior to full compression, the fusion energy per pulse is given by equation 8, and for the assumed parameters yields E equal 14 megajoule. The REP rate R is determined by the wall loading limits, taking advantage of the translatability of the burning FRC. The compression section can be made much longer than the FRC so that the drifting FRC deposits the fusion energy along a series of compression coil sections. Alternatively, the FRC can be merged and brought to rest in a different part of the elongated compression chamber with each pulse. In other cases, the REP rate will likely never exceed 2-4 Hz for average power of 40 to 60 megawatt in order to maintain the average neutron fluence below 4 megawatt per meter squared. The low frequency minimizes the pulse power issues as well as any pump out concerns. A low total fusion yield would at first seem restrictive. It does, however, have several advantages, with eventual fusion power plant power output in the 200 to 500 megawatt range. The pulsed FRC reactor can be modularized. The investment intensive energy input and full recovery system can be used to power multiple relatively inexpensive, easily replaceable burn chamber. This will be particularly important in the easily stages of development when reliability and maintenance schedules will be less well understood. In summary, with the repetitive and efficient generation of FRC plasmoids brought to high temperature and density as they are injected into the burn chamber, a compact low-cost fusion neutron source can be achieved. At a minimum, it would be an achieved source for fast neutron-based applications such as isotope production, fissile for breeding and fission weight transmutation. The expectation is with the successful demonstration of a prototype scale device, a viable alternative for fusion energy production can be rapidly developed at an affordable cost and will super a renewed urgency to perform the required reactor development on a timescale that will allow fusion to be a major player in the world energy future. Thank you.